Okay. Good afternoon. Today, lecture number 12 of our optimization course. So we will have two topics. First is so-called sequential subspace optimization method. It's an extension of conjugate gradient for nonlinear optimization. And the second one is Quasi-Newton method. So both of them are dedicated for large-scale problems. So the first of the methods is sequential subspace optimization method. It can be considered as a natural extension of conjugate gradient method. As you remember, in conjugate gradients, in every iteration, we got optimization over so-called expanding manifold of all previous directions and gradients. And here, in this method, we will do it explicitly because we deal now not with quadratic, but with general nonlinear function. So suppose we would like to optimize smooth nonlinear function of n variables. And as usual, our notation gradient is gk at iteration k. And what else we will use? The direction which brought us to the point xk. So it was dk minus 1 is equal xk minus xk minus 1. And so there is another formulation of conjugate gradient method. One can say if I have a quadratic function and I have gradient and I have a previous direction, I can say just minimize my function in the subspace, in affine subspace of these two vectors, and this will give me a new point of my algorithm. And now we just generalize this concept. Let us build a matrix, I will call it pk, with columns containing our directions. So one of the column will be current gradient, another dk minus 1, but we can also include more previous directions, for example, and even more previous gradients. For example, dk minus 2 and so on. And so if I will write formally what I do in iteration k of my algorithm, I just will consider a function of xk plus p alpha. If you remember linear algebra, this is sum of alpha k pk, where pk columns of matrix P. And I like to minimize it over alpha. It means that I minimize over affine subspace which pass through the point xk and spans direction of columns of matrix K. And if I take argmin, I will get alpha k. Sorry. Alpha k is argmin. And of course, xk plus 1 is xk plus p alpha k. So algorithm, the concept of algorithm is extremely simple. The only remark, we need perform here multi-dimensional optimization at every step, despite the dimension may be small. The smallest version when we have only two vectors. So alpha is two-dimensional, but it may be larger. And one can say that our iteration is more demanding than, for example, iteration of conjugate gradient methods, which requires only line search. But now I will show you an important example of functions which we meet almost everywhere, where this subspace optimization will be cheap. Okay, so I'll bring you an example where subspace optimization may be done very efficiently. In many applications, our function f of x has a form like this. It's some function phi of ax. So phi is a function of vector argument, but it's cheap to compute. For example, it's sum of phi I of its elements, but maybe also different. And A is some linear operator, some large matrix, and so on, which is difficult to compute. And the most of computation in phi of ax is in this multiplication. And what I'm going to show is that in subspace optimization, you really don't need additional multiplications of A. So I'll write it formally. Ax costly to compute, and phi cheap. So in subspace optimization, I need to compute function of xk plus p multiplied by alpha, which is, I just substitute phi of axk plus ap multiplied by alpha. And in order to do subspace optimization, I should compute this function for many values, many different values of alpha. So the idea is simple. First of all, pre-compute this. And as we will see, it even don't need it to be pre-computed explicitly. And pre-compute this. I may define this matrix as matrix R. And during my optimization, I just substitute alpha and multiply it by a matrix which is relatively small, at least in one dimension. So the operation become much cheaper. More than this, at every external iteration of the method, we change one column in matrix P, because you remember we keep all previous direction and only add the new gradient and throughout the oldest direction. So in order to have this product A by P, multiply A by matrix is like multiply it by every column and put it in the corresponding column of R. So we need to recompute only one column of R. So I just will summarize. R can be pre-computed, for subspace optimization. And after we did our computations and optimization, sorry, and computed alpha k as optimal vector, even to compute a multiplied by x plus 1, which will prepare optimization in the next step, I don't need to compute it explicitly. I just need a kaful xk plus r, which I already have, multiplied by alpha k. So actually, at every iteration of subspace optimization method, I need just one multiplication of matrix A by a new column of P. And that's all. Let's also write how gradient of phi with respect to alpha looks. So gradient with respect to alpha phi of A xk plus r alpha. I will write here formula, but at home I will ask you to develop it, which is rather easy by differential calculus, which we learned in the beginning of the course. So it will be just R transpose by gradient. Let's denote all this like U, gradient with respect to U, phi of U. And similar, I even can compute Hessian, alpha alpha of phi. Again, I will write A xk plus r alpha. And it will be just R transform, R transpose Hessian of this inner function, u phi of u, and multiplied by r. So as you see, those operations are cheap. Here you still will need, if we told that x is n-dimensional vector, so the columns of R are of size n. So to compute R transpose R, you need n multiplied by number of columns of R in square. But again, so Newton step may be demanding, but still one need to look for compromise between number of steps and the cost, and it may be very reasonable cost to do, say, 2 or 3 Newton steps at every subspace optimization. Okay, so subspace optimization method was, which we just described, is very good for very large problems. Problems which may have hundreds of thousands, even millions of variables, because the only thing we need manipulate with few vectors of the size of x. On the other hand, if you have a moderate size problem, which means for modern computers, it's like several thousands variables, where we can keep a matrix of Hessian. There are methods which called Quasi-Newton methods, which can take advantage of this. Still, we will not compute the Hessian explicitly because to compute it may be costly, and also to solve system of linear equation is like n-cube operations. We will consider alternative methods which requires about n squared operation, maybe 6 or 8 n squared operations. And it will use the approximate model of the Hessian. So, again, as before, we consider a problem, minimization of Rn of smooth function, and gk is gradient at our current point. And we will use approximation of inverse of Hessian, bk. It's current approximation to inverse Hessian. H minus 1k, which is Hessian inverse. And we will take care that B, our approximation, will be symmetric and positive semi-definite, or positive definite, in order, like we told when we developed Newton method, in order to keep our current direction to be direction of descent. And our algorithm is very similar in main part with the Newton method. So we compute approximate Newton direction. Sorry. And its dk minus inverse, and here is approximate inverse of Hessian multiplied by gradient k. And update x. Mean x k plus 1 by line search is equal xk plus alpha k dk by line search. Which may be inexact. Like backtracking line search with Armier rule. And this is an advantage over conjugate gradients method, which requires exact line search. And then, when we advanced, we can compute gradient in new point. So we compute gk plus 1 gradient xk plus 1. And then, by some formula, which I will explain right now, we update our model of inverse Hessian based on our new information. Hessian is very tightly related to the thing how gradients are changing with shifts by x, because it's like information about second derivative says how first derivatives should change. So I would just write symbolically here, bk plus 1 is some update formula which will take old approximation bk, which will use our shift in x, xk plus 1 minus xk, and we'll also analyze how gradient changed, jk plus 1 minus jk, and on base of this information we'll suggest what will be new approximation of inverse Hessian. So this is more or less a general scheme, and now we will tell how to do this update. Okay, so how to approximate Hessian or inverse Hessian? We will start with Hessian, and then we'll go to inverse Hessian. So we'll first denote the differences we use. So pk is equal xk plus 1 minus xk, and qk is gk plus 1 minus gk. And now, so what kind of information Hessian can give us? If you remember from definition of Hessian, h dx is equal to dg. So it's for, one can say for very small changes in x, this will be a very small change in g. But if one considers, for example, quadratic function, then even large change, g is linearly dependent on x, so even for large changes in x and g, it will be correct. So, and in our terms, we think in the beginning about quadratic function, so we will ask our Hessian approximation multiplied by dx. This is p. pk is equal to qk. And this requirement even has a name, so-called secant equation. And now one can ask, what would be the simplest way of updating Hessian? I can say, for example, I have a previous approximation of Hessian. And a very simple update of matrix is so-called rank 1 update. Rank 1 matrix is outer product of vector column by vector row. And I will just ask, what is a rank 1 update of my previous model of Hessian in the way that it will satisfy secant equation for our last step, last differences. So in other way, I will look, hk plus 1 in this simple form, hk plus u v transpose, column by row, and this I will call rank 1 update. So what I am looking for is HK, I write it just once more, plus U V transpose PK is equal to QK. This equation. So I can open parentheses and I will get, and you will check whether I am correct, U V transpose PK. I use this one. And of course, if I have a multiplication of several entities, I can change parentheses. Why I am interested to do this? Because V transpose PK is scalar. So what left, QK minus HK PK. So from this, I get formula for U. U will be equal 1 over V transpose PK Q K minus HK PK. And so this formula for U, and what is V? We have just one equation, and that's why any V, just we need this should be non-zero, yes? And V, any vector, just non-orthogonal to PK. Non-orthogonal, I will write in this way, to PK. So we have another degree of freedom, but it's useful. It's useful because I can say, let me preserve symmetricity of this expression, because I know the Hessian is symmetric matrix. So how I can keep it symmetric? If the second term will be symmetric, it means that V will be a copy of U, or maybe a copy of U with some scalar multiplier, then it still will give symmetric. So to preserve symmetry, I will write it in words. Symmetry. So V should be proportional to U. And U is this expression multiplied by this scalar. This is a scalar. So I can choose, for example, U as this expression. So I can use V is equal to Q K minus HK PK. And in this, and just to keep a compact expression, I can rewrite U is just some scalar, 1 over V transpose PK multiplied by V. Okay, this is my V, and if I summarize all this together, I get finally HK plus I have U V transpose. I'll write and you will see that I wrote right thing. 1 over V transpose PK V, it's expression for U, and multiplied by V transpose. So here is all what we need for our update, okay? V, U, and update of H. So we had this formula for Hessian update, but actually we are interested in inverse Hessian. So one could first compute Hessian and then solve Newton equations, which is expensive, but we can actually compute inverse directly. One can use, first of all, there are formulas. If you have a rank 1 update of matrix, you can know what will be update of its inverse, or even limited rank update of matrix. And I will just refer you to Sherman-Morrison formula. Sherman-Morrison, double R, I think. So it's it will give you B inverse, BK plus 1 inverse. If you have HK plus 1 inverse. And I will say rank 1 update. I will not give it here, but you can find it in books, for example, Bertsekas books on nonlinear optimization. Here we will do much more simple thing. If B is our inverse, so let's think we multiply by inverse of H. So we get PK is inverse multiplied by Q, if I multiply by the same inverse. So inverse I denote as BK plus 1 multiplied by QK is equal PK. Again, how I got this formula? I just multiply BK plus 1 left and right side and use that BK plus 1 is inverse of HK plus 1. But if you compare these two expressions, you see that they are very similar except of P and Q switch their roles. And that's why I can just rewrite this formula only writing Q in places where was P and P in places where was Q, and check that I am right. So V will be PK minus BKQK. And B instead of H, yes? And BK plus 1, BK plus 1 over V transpose QK, V transpose. Actually, we don't need U now. U is only auxiliary in our derivation. So this will fully express our update. But still, this will get us more close to the efficient quasi-Newton algorithm, but still it's not the most efficient one. There are many small things which one should take care of. For example, to provide positive definiteness of matrix after every update. And all these things were taken in consideration, and people got the algorithm which is considered as a state of the art, which is called BFGS, and which will be on the next whiteboard. Like I told, after people take in consideration many different demands to the update, like being symmetric and being minimal, being as close as possible to the previous version of approximate Hessian. So they came with so-called two-rank update of the Hessian, which finally will give this formula for inverse Hessian, for B, which is used in computation. So what, and this family of quasi-Newton is called Broyden family, and one of important methods is so-called BFGS. It's Broyden Fletcher Goldfarb and Shano. And another modification, which is called DFP, it's Davidon, Fletcher, and Pavel. Okay, so let me say what is the notation. So like before, we denote those differences, Q and P, and then SK is a product of our previous approximation of inverse Hessian with Q, and those are scalar products of corresponding vectors. This is Q. And another vector V, and here is this relatively complicated formula for update, where Xi is a parameter. When Xi is 1, so this whole formula is whole formula is in use. So it's when Xi is equal to 1. We have this formula, and 0, this formula. So what you have here computationally, not so expensive stuff. So here you just compute two vectors, and here are outer product of vectors. So it's like n square operations. So you have n square, and n square, so 3 times of n square and 1 more matrix. So it's 3n square multiplications here in this formula, and the same additions and some multiplications and additions here. I think approximately it's 8n square operations or multiplications all together. And in practice, this version, which is called BFGS, it's definitely the most popular, and you will find it everywhere, including MATLAB optimization toolbox function fmin-anc, and it's really a method of choice when your number of variables is reasonable to keep this matrix in memory of computer, maybe till several thousands of variables. And when computing your function and gradient is not very cheap, because otherwise it still may dominate very much function computation, and you will like to switch to conjugate gradient or to subspace optimization. So, and just to say a few words, so this update formula provides us the following property, this secant property like was in our rank 1 update. So bk plus 1 multiplied by qk is equal to pk. And it provides positive definiteness, bk plus 1 positive definite. This is sign for positive definite matrix. And symmetric. And it minimizes, in some sense, I will refer you to book, for example, of Bertsekas, a norm of update, norm of difference, bk plus 1 minus bk. So when people developed this formula, they took into consideration all those properties. And one more remark, which is very important, to keep this property of positive definiteness at the line search stage of the algorithm. If you deal with the non-convex problem, you should take care about just I will write it, that absolute value of derivative will be smaller after line search than before. I mean directional derivative. Let me write it in the words because it's very important to keep bk plus 1 positive definite. We need line search. F tag dk f prime dk directional derivative of our objective function in previous direction before we did this computation. In starting point of line search should be less than f prime dk xk plus 1. Just let me think about signs. So So directional derivative is negative. It should be less negative. It should be less. So really it's steeper. It's more negative in the beginning than in the end of line search, so the sign is correct. It's larger in absolute value, negative number in the beginning of line search. And one more word about initialization of the method. If you don't know anything about Hessian, just start with identity. Or if you know much about Hessian, start with some approximate as much as you know, and in between, if you know diagonal of the Hessian, start with diagonal matrix of the inverse of the diagonal of Hessian. So as much as you know, try to put to this consideration. Or sometimes you already optimized the function and you changed some parameters and you want to continue with optimization. Use the result of previous optimization, and we will use it for constraint optimization, for example. Okay, and another property, very important, if we apply this BFGS Quasi-Newton to quadratic function and perform exact line search for quadratic function, it will be analytical. Interestingly, we will get the same trajectory as conjugate gradient method does. And we will solve quadratic problem exactly in n steps at least. And after n steps, we will have exact Hessian. So when f of x is quadratic, we get exact Hessian. Exact Hessian after n steps. After n steps, and is equivalent to CG, is equivalent to conjugate gradients, CG, when B0 initial matrix is identity. Let's say property 1, 2, and 3, what I should say, when f is non-quadratic, in practice it's usually converges in less iterations than conjugate gradient requires. Quite often, you never can guarantee in nonlinear optimization that for every nonlinear function, method will be better because some can invent a nonlinear function which first iteration which leads to solution for gradient descent, and that's all. So f non-quadratic Quasi-Newton usually faster, typically faster than CG. And another important advantage, it doesn't require exact line search. usually rate of convergence, we told that, for example, for gradient method for nonlinear function, linear convergence rate, and for Newton quadratic convergence rate, and for quasi-Newton, when Hessian is non-degenerative in the solution, is so-called superlinear convergence rate. How can one express it? For example, x k plus 1 in some norm minus x star divided by xk minus x star, again in some norm. So if we would have linear convergence, we would have some constant in limit. And superlinear means this in limit it goes to 0. So this is a general recommendation. If you have not too much variables, not too much more than several thousand, just first try Quasi-Newton and then see whether other methods can improve. Thank you.